Hello, and welcome to this Beyond Clean virtual conference. The speakers for today's conference, the sponsors for today's conference, and the Beyond Clean team are all so excited that you're here. If this is your first time joining us for a Beyond Clean virtual event, I want to call your attention to a couple of event functions. All of the windows on your event screen are movable. You can shrink them, you can enlarge them, you can move them, whatever you need to do to create the event feel that works best for you. In the upper right corner is a resources tool. Download conference sponsor information and the resources and links that your speakers have provided for you, as well as instructions for obtaining your CE certificate for the day's event. On the bottom left, you will see a Q&A or question and answer tool. Any questions that you have for the speaker during each session can be submitted to them using this feature. Our speakers today will bring you a wealth of knowledge, and all of their information can be found in the speaker bio tool on the right side of your screen. Along the bottom are the icons for each of the windows as well. Clicking these will minimize and maximize each window. This will be an action-packed conference, and there will be 15-minute breaks between each of the sessions. So feel free to grab a snack, check on the dogs or the kids, assemble a tray, do some jumping jacks, whatever you need to do before joining us again.
All right. Good morning, everybody. Welcome, welcome, welcome. It's wonderful to have you here. My name is Lindsay Brown with the Beyond Clean team, and I am so excited to welcome you to a fun and exciting day of learning. Today, we are wrapping up our SPX 2021 Virtual Vendor Expo with the Prove It, a Spotlight on Sterile Processing Quality virtual conference. Without the support of our event sponsor, 3M, today would not have been possible. So a huge thank you and shout out to the team at 3M. Like I said, my name is Lindsay Brown from Beyond Clean. On behalf of everyone on the Beyond Clean team, we wish you an enlightening, a productive, and a celebratory day of virtual learning. Here to share this amazing day with me is my colleague, Brett Norton. Welcome, Brett. I'm so excited to be co-hosting this event with you and co-hosting your first Beyond Clean virtual event. How are you this morning?
I'm good, Lindsay. Thank you. I'm really excited to be here. It's great to be a part of this event, and we've got a great lineup of speakers. I've been honored to get to know some of them through the past several weeks, so I'm really excited. Looking forward to this day. Hello, everybody. Thank you for tuning in for what will be an incredible day of learning. I'd like to call to everybody's attention to the features on your screen. All the windows that you see are movable, so feel free to shrink, enlarge, or move them around to make your event experience fit your preferences. On the lower left, you'll see a Q&A window. Throughout each presentation, you can enter questions for the speakers. And in the upper right, you will see a resources window where you'll find additional resources to download and access provided by our speakers and sponsors. We're excited that you have chosen to kick off your weekend by joining us on this Friday. Happy Friday, everybody. I understand that you probably have a lot going on between work and home, and I just want to say thank you for being here, for being dedicated to education, for doing something that will help you grow as a sterile processing professional.
Yes, and I want to echo that. Thank you, everyone. We know it takes a lot to join a virtual event on a Friday for multiple reasons, but we are so glad that you're here. So you all can sit back, relax. If you need to start a sterilizer load quick, certainly feel free to do that. I know some of you are joining us from work, but without further ado, it's time to get this event started. Our first speaker I've had the absolute honor of getting to know this morning, which is awesome. Pavel's reputation precedes himself. He is such an awesome asset to this industry, and I'm excited to introduce you all to him. Pavel's the managing director and a research and development engineer at Aseptum. He is an experienced engineer with a passion for researching and creating clever solutions. He holds a degree in mechanical engineering, automation, robotics, and business. No big deal. Wow. He's dedicated to evaluating innovative solutions to solve the decontamination challenges for complex surgical instruments. I'm so glad people like Pavel exist in this world. Pavel's going to share his insights on the importance of reusable surgical instrument optimization and the impact that standardization has on the instrument cleaning process. Without further ado, good morning, everyone. If you're tuning in and it's morning for you, kicking off this conference on quality is Pavel. Pavel, welcome.
Good morning, everyone. I'm absolutely delighted to be here. I know that it is an early start for some of you, so I'll do my absolute best to make it worth for you. And I know that we are also starting with a subject of optimization of cleaning processes of surgical instruments. And this is a vast field, and we are going to talk about many different aspects of that process as such. And I really encourage you to sort of join in, ask questions, and let's have a really nice and productive presentation and conversation between ourselves. I will aim to answer all of the questions that we'll get, and because we have quite a lot of content to go through, just whenever you stumble upon something that requires further explanation, please just drop your question in the Q&A, and we'll either address them right at the end of the session, or I will then respond to those individually afterwards. So I promise I will not leave anyone puzzled at the end of it. And I'm also absolutely delighted that we have such an international audience. I'm broadcasting at the moment from Inverness in the Scottish Highlands, where we have surprisingly an absolutely beautiful spring day. So I'm really happy that you are all here. I've had a glimpse at the attendee list, and it's absolutely fantastic to see so many names and to also see so many names that I know, which is absolutely fantastic. So without going into further details, let's get on with our presentation, and this is the agenda for today. So we are going to talk about the process optimization, and I'm going to first of all introduce what it's all about. And then we have the sort of vital components that we have to consider whenever we are talking about process optimization. So the test soils, so the substances that we use to simulate dirt on surgical instruments. We are going to talk about the technical characteristics of our washers and what makes them clean or not clean very well. We are also going to talk about process challenge devices and other tools that we can use to monitor, improve, and verify our processes. And at the end, I will also show you some of the sort of techniques and strategies that we use on a daily basis in our laboratory, working with different types of chemistries, washes, and processes, and how we try to squeeze the best value out of the process that we have. And obviously, at the end, we'll have the Q&A session. So let's crack on with this. What I wanted to stress at the very beginning is to say that optimization is a very complex process, and it's a complex process for a reason, because we are not going to talk only about your washers or washer disinfectors, because the entire cleaning process is a lot bigger than that. And unfortunately for us, it's also the fact that this is a serial process, where one action leads to another action, leads to another action. And if anything happens to the result of any of those actions preceding the final inspection and verification, the final result is not going to be great. And we have to remember that cleaning starts as early as the preparation. So taking the instruments apart, making sure that we get our sets properly ready for cleaning. Then we have our pre-cleaning, and you know probably even better than I do how many different IFUs and how many different ways of pre-cleaning are there, and you have to get on with this, unfortunately, even before the machines end up in washers for their automated cleaning. And the last element of the puzzle is the inspection. So what I want you to sort of think about whenever we are going to discuss the optimization of cleaning processes is to think about all of those elements, because they all complete our journey of a dirty surgical instrument through the decontamination process to achieve a clean and safe to use tool. So what is the goal? Why are we doing it? So you've been probably hearing about optimization of processes at different conferences. And over here, I wanted to stress out that for me, always the goal is to make sure that first and foremost, we have a super effective process. Super effective means that as a result of it, we get clean instruments. And this is the most important element of that puzzle. What we do then is, once we've achieved that goal of having a clean instrument, we can look at improving the efficiency of the process. And by improving efficiency, we are talking about saving the resources that are required to achieve this end goal. So from that perspective, we can think about saving time. And saving time is not only about making our washer processes shorter. This, I think, in respect to the entire process we've just discussed, this is probably the least effective way to optimize your process. Whenever we can save time, especially the time where manual operations are executed, this is where we can properly optimize the process. This is where we can properly find value by cutting the time of manual labor. So it's either less time spent on preparing the instruments, less people making sure that the instruments are getting loaded into washers properly, less PPE, less use of water, less use of chemistries, and so on. So this is the entire premise over here, not to look only at the time of your washer disinfector, but look at the entire thing and see where the costs really are. So, on that note, please always remember that we are going back to that previous slide where we are considering the cleaning process as everything that happens from the beginning to the end point where we do verification. And this is a great thing, because I've had a chance to discuss this approach with Petra Labonte, one of my colleagues from Germany, who is also helping hospitals be more effective. And this is something that she's been stressing out, that she sees the process almost like a journey. So this is something where we have to consider every single step to find out how we get from point A to the end goal of having clean instruments. So that's what we are starting with. So now, once we have the context of what that optimization actually is, we have to jump into a heavy topic of test soils. And you'll be probably wondering at this stage, why are we discussing test soils? You know, we've been looking at, the entire process, but now we are jumping into something that is very specific. And we are discussing test soils for a very simple reason. Test soils become a tool that we use to verify whether all our effort of cleaning those instruments was worth it. And it's unfortunately based on the performance of those test soils. So those substances that we either inoculate instruments when we are testing instruments individually, or those substances that we see on process change devices, it's based on their performance, it's based on the behavior of those test soils. We are actually classifying a process to be good or not. So they are actually a critical, really critical ingredient over here. So when you think about those substances that we use on process change devices, it's natural that we would sort of hope they will behave the same way as contamination after surgery behaves on surgical instruments. How do they correlate? Are they adequately representing the type of a challenge that the process has to remove it? And if you think about it, test soils are super complex substances, because at the end of the day, even if you think about blood on its own, it's composed of many different elements. You have proteins, carbohydrates, you have lipids, and it's not only that there are 3 different main ingredients. There are thousands of different types of each individual ingredient, and unfortunately, from our point of view, when we consider decontamination, they all behave differently, because we can have proteins that are thermolayable and withstand very high temperatures. We have proteins that can adhere very strongly to surfaces when they are hydrophobic. We have water-soluble proteins like hemoglobin, for example, that dissolves in water really easily. So all of them matter, and how we approach the problem of test soils is therefore really, really critical. Because at the end of the day, you would like to know, or you would like to have that hope that if you've used a PCD or an inoculated instrument with a test soil and your process delivered a clean result, you would like to hope that this means that everything that goes through that washer also comes out clean. So that's why we, when we talk about test soil, this is not just a dry subject, but it's something that is critically important from our point of view. So let's think about what makes those test soils representative. By representative, what I mean is, how do we make sure that those test soils behave like our real contamination? So I've mentioned about the complex structure already, but it's also how they are processed, because you very well know by now that a very well dried on blood or contamination on surgical instruments is a lot more difficult to remove than fresh one that didn't have the time to dry. So the level of dryness is really important over here. What type of surfaces were made dirty with that soil, and you've seen now that we are no longer only talking about stainless steel surgical instruments, but we have different materials that are being brought to theaters at the same time, and all of it has an impact on how well that test soil adheres to the surface. And there are a number of different elements that play a critical role here. Temperature, obviously, and humidity, but also the presence of other chemistries. You know very well that there are a great number of products that you can use to, for example, keep your instruments moist right after surgeries before they come to the decontamination department, and all of those variables make a difference. So what I want to stress out really at this stage is that this is super complex, and there's so many different variables over here that one needs to consider, that it takes a lot of effort to make sure that you have something that is truly representative. One thing that I'm going to show you in a moment, and we are already seeing some pictures here, is most what I'm talking about is coming from our own experience in the laboratory, because we develop and make new test soils for process change devices. So we have tried many different things, and a lot of what we have learned comes from experience of of failure as well, because when we've been trying different approaches, you could compare even the same type of test soil applied to different surfaces, applied in different conditions, creating very different end result. On the right-hand side, on the bottom, you have a lovely picture that was taken from a publication by Markus Verl. That was in Central Sterilization, where they've been trying to create a fibrin-based process change device. And you see over here how very different the test soil looks, when the only difference they've tried to capture over here was the humidity in which the test soil was allowed to mature, so to say. The picture above it is one of our test soil being inoculated on surfaces. And on the right-hand side, technically, they've been done in exactly the same piece of equipment. We've got a robot that creates this nice shape over here, but you see that the one on the right-hand side looks very different. And the key to what happened over here was, again, different temperature of drying and surface preparation. So you can see that the same type of substance behaves in a very, very different way. We've done previous studies to figure out what sort of surface preparation, especially with stainless steel, makes it sort of more susceptible to adhere for different types of contamination. So we are using the worst case scenario approach with the PCT samples that you see over here to make sure that we identify the type of surface finish that makes it particularly easy for blood and tissue fragments to stick to. And it's super interesting from the laboratory point of view when you see how little can change and what difference it actually creates at the end. So the lesson from this is, again, we have many, many different variables that create a test soil with certain characteristics. And this is one thing that I wanted to show you because this was an experiment that we've tried to conduct to simulate what will happen when you dry blood very quickly on instruments. So you can see that on the left-hand side you have a nice sort of round shape. The soil looks consistent, and in the middle we tried an approach where just blood was dried very quickly. The surface was warmed up, and soil was allowed to very, very quickly dry on it. On the right-hand side, you see we had an entire sample made of it. We had a little video over here that I don't seem to be able to play, but don't worry about it. The idea was here that soil was so brittle that when we tapped that sample against the table, 95% of what you see on it simply came off because it was so brittle. And you know from experience that we don't really see this often on surgical instruments. But the only thing that we've done over here was to dry it very quickly. So this is something that I'm hoping now there is a picture forming in your heads about how critical it is to have something that is representative, but also something that represents that worst case scenario where you think about the soil that can happen, can provide us with a true challenge for our cleaning process. And talking about the test soils that we use for verification or validation of cleaning processes, we have audiences from around the world over here, and you'll see that in different countries we, for example, have entirely different substances that we use for technically the same purpose. So they'll all create different results. The really nice example is going back to that article from Marcus Vail from Central Sterilization, when there was an attempt to create a fibrin-based process change device. This was a really interesting research where fibrin was identified as this protein that sticks very strongly to surgical steel, and experiments that this article explores shown us a method to get there. But what was really interesting is, if you think about the process of achieving just a piece of stainless steel with a fibrin layer left on it, it actually involved almost a pre-cleaning step where hemoglobin, so the red pigment that we see in blood, that's what makes our blood red, that was washed out in the process. So they've actually produced test pieces that were partially washed just to expose us to that fibrin layer that is even more difficult to clean. But that also proves that that red color, in comparison to other types of proteins that we find in blood or tissue fragments that very often end up on surgical instruments, that red pigment is relatively easy to remove. It dissolves in water. So this is also a really important lesson here to remember, that we are used to the fact that you look at an instrument and you see no red marks on it, so you think, oh, it's clean. But that, unfortunately, couldn't be further from the truth, because once hemoglobin is removed, we don't see the red pigment. What we see is, like in this particular case of the fibrin-based test soil, we just see this sort of opaque layer of contamination. And if you think about it, look at the types of surface finishes we have on our instruments, especially handles. Whenever they are lacerated or engraved to improve grip, you'll find out they will have a very different surface finish. It's not anymore this nice shiny surface, but it's almost dull. Sometimes it's scored further to improve handling. And it would be almost impossible to see that, the fragments of opaque, semi-transparent layer of proteins. And that is the difficult bit about evaluating whether particular solution, particular soil was good or not. And that leads us very nicely to the question of how clean is clean. Because at the end of the day, if we removed most of our hemoglobin and our eyes are no longer clearly seeing contamination, how do we know that something is clean? So there are many methods that you can use, and there are different markers that we use to identify whether the surfaces are free of contamination. Proteins are one of them, because all of the body fluids, all of the tissues, all of the cells in our body contain different types of proteins, so it's a good universal marker. Total organic carbon, then you can look at carbohydrates. There are also standards that are giving us limits on hemoglobin, but on that picture that we've just seen, I've just shown you that hemoglobin on its own is the first thing that gets removed because it's water soluble. So it is quite tricky to say whether hemoglobin on its own is a good marker to tell us whether our process was actually effective or not. And then you're left with ATP, and this is another sort of controversial market to look at, just because it's looking at things that are very specific, and most of our washer disinfector cycles end up with a disinfecting stage where most microorganisms get killed. So whether ATP is a good marker over here or not, I'll leave it for someone else to debate. But it's good to consider that. It's good to consider all of your options and see what we have available and how you can actually evaluate the cleanliness of either your instruments or process change devices. Because at the end of the day, if you think about any form of optimization of processes, we have to first look at our current state. We have to first measure where we are to be able to identify whether we can improve, whether we need to improve, or how much do we have to improve. And those markers are a really useful tool to do it. So there's one element that I wanted to show you over here that we have done during our research of test soils. We've been looking at composition of blood and brain tissue from sheep to find out the diversity, or what the diversity of proteins in those tissues are. So you have two lovely pictures of gel electrophoresis. It's a method where you split your substance. So if you have different types of proteins in your substance, gel electrophoresis is going to split them by weight. It's a very nice sort of physical chemical process where charged protein particles are put in an electric field and they simply travel. So the light ones travel a different distance to the heavy ones. So after some time, you can look at it and you can see how many different sizes of proteins we have in our substance. So if there was one substance made of only one type of protein, there would be just one horizontal line. But over here, we see hundreds, if not thousands, of tiny little lines. We've basically shown here that blood and tissue are not just homogeneous substances. They contain thousands of different types of different elements, and they contain different types of proteins as well. And when I was talking to you earlier on about the physical characteristics of those proteins, in those thousands, you'll find the whole plethora of those. You'll find those who withstand heat. You'll find those that stick to surfaces. You'll obviously find the ones that we see, so hemoglobin and so on. And it is really important to remember that if you think about real contamination of instruments after surgeries, where there is blood, tissue fragments, body fluids, and so on, we have all that mixed there. So whenever you are going to verify your process later on, you have to consider the fact that it is only going to be representative properly if you have huge diversity of those elements, of proteins, lipids, and carbohydrates, because that then challenges your process, challenges your chemistries, because chemistries also, they break down different elements in a different way. And even different types of proteins, because of their physical shape, they are broken down by, for example, enzymes in chemicals in different rates, in different time. So this is really critical at this moment to consider that I want to have a test soil or a substance that I'm using to simulate dirty instruments that contains all of those different types of elements, so I can properly verify my process. We've been doing hundreds of different types of experiments, and this one was done together with the University of Highlands and Islands here in Inverness. We've been doing that entire study of proteomics and mass spectrometry of test soils to see whether we can easily spot a difference between different cleaning processes used on the same test soil. And one thing that was really, really interesting here, we've used for comparison 2 different cleaning chemicals. They were used as the manufacturers were recommending. And what you see over here is chemical 1 versus chemical 2. It's not only the fact that you see that obviously one seemed to perform a little bit better because you see less of those lines, but it's also the case that you simply see different lines. And it's the fact that they are different tells us that some chemicals will remove from that huge pool of different proteins some part of it, but leave something behind. And the other chemical is not only going to be better or worse at removing that first part, it's just going to remove a different set of proteins. And that was something that gave me an idea very early at almost at the outset of our research into test soils, that only by having this huge diversity of proteins in your sample, you can make sure that your process is properly scrutinized. Because if it was only a couple of different proteins here and there, we would really struggle. So, to sum up the test soils, I know that it's been a challenging one for you, but I'm hoping that now you understand why I spent so much time discussing it. So think about whenever you put a test piece in your washer that is supposed to tell you whether your process is good or not, ask yourself, what's its composition? How was it prepared? Is it repeatable in terms of its performance? And lastly, think also, because we have a number of different products, about the synthetic products. What are they made of? How do they represent the real contamination that we use on surgical instruments? Because if you don't capture the essence of this super complex structure, like the natural contamination, we might be actually losing that battle. Because if you are using a wrong non-representative test soil, you may be passing a cycle that in fact is not actually removing everything from your instruments. Excellent. We've closed the probably most challenging and the most difficult part, and now we are going to look into technologies and washers, the subject I particularly like because I developed those. So it's also another element that makes it fun when you sort of discover how good or bad they are. But from the perspective of cleaning, let's look at the first and the most fundamental thing. Some instruments we have to clean inside. Think about all of the instruments like suctions, for example. If you have spray arms, the best spray arms in the world, spraying the water all over your load, do they actually clean your suctions inside, especially if they're quite long? I would say most probably not. So you know already that we have those clever machines that flush them with the mixture of water and chemicals during your process. But the problem we are getting to is the fact that the process of cleaning something inside versus cleaning something on the outside is very different. And this is talking from the technical, physical point of view. And the problem is that whenever we are going to evaluate our process and sort of see a nice clean PCD after the washer disinfector process, we also have to think, did it actually test what I wanted it to test? Because if I've only tested or simulated a load that gets cleaned with spray arms, were the insides of those instruments that require flushing, were they cleaned at the same time as well? Because if they haven't been cleaned at the same time as well, then what's the point? So this is the one first distinction that I wanted to present over here. So look at the spray arms first. Spray arms take water from your system that delivers it to your chamber and spread it around your instruments. But again, they are simply tubes or objects with holes through which water is pumped. And as you can see on that picture, this is from a dishwasher, so don't take that too literally. But you can see the concept over here, that you simply have jets of water shooting out of a spray arm, but this is not consistent. Not every point about this spray arm gets exactly the same amount of water. So whenever we are talking about machines with very good mechanical cleaning, we have to consider that at the end of the day, we have a spray arm that shoots water out. And maybe like in the case of this particular one, look at the middle of that spray arm. There is no water coming out of it whatsoever. So how is the poor instrument that sits right above it in the washer, how will that get cleaned? That's a good question. On the right-hand side, you have another really nice diagram because you see the grayed circle shows you the area that a spray arm covers directly. So right underneath that or above that, you'll have instruments being exposed directly to the jets from the spray arm. But most of our washers at the moment can load 3 regular DIN baskets on, so they are not square or not round. So what happens to the area that falls outside of that grayed out circle? That area receives less water. And in the brutal way, less water means less cleaning. And now when you think about the corners, that is the Achilles heel of some washers, because if the water doesn't penetrate those corners very well, and think also about the fact that it's not only from the above, it's from all of the directions, because all our surgical instruments are 3-dimensional, so they have to be cleaned all the way around, not only on the top. So that's something to consider, especially when you're loading instruments. And the only way to know how well your washer cleans it is to test it, how well it cleans in those corners. So I'm hoping now that you're properly motivated to run to your departments and throw some test pieces into corners of your washer and see what happens. Well, I would. Second element over here that is super critical as well is the cleaning on the inside. And this is something that I always like to compare to a river flowing through countryside, because sometimes you see nice and calm water, rivers really, water sort of runs slowly through, we call it a laminar flow, and then you sometimes see the mountain rivers where water seems to be flowing in all directions at the same time. And again, this is depending on the speed of that water going through the river. And if we truly want to have good cleaning of the insides of the channels, we really want to have that fast flow with turbulence, because, as you can see as well on the diagram on the right-hand side, you'll see that in our case, what we are interested in is removing stuff from the walls, not from the inside of that tube, removing it from the walls. So turbulent flow is definitely going to help us on that journey. So this is just something to consider. But again, from the technical point of view, if you think about how your washer does it, you have to think, how am I connecting my instruments that require internal cleaning? Is there sufficient water going through it to clean it? And is my process performing well enough so I can assume that if my load went through the process, I have the inside as well as the outside properly clean? And again, if you don't test it, you'll never know. So I'll talk briefly about process change devices and how to use them. This is something that most of you are using on a daily basis, but I'll simply jump to certain characteristics that will make your process testing and process control better and easier to improve. So if you think about the concept of testing, we've just discussed the characteristic of washers that, cleaning is not uniform, so you would like to somehow evaluate in its entire volume where you have those areas of suboptimal cleaning. And ideally, from the patient's perspective, you would like to test every single instrument. But that is completely impractical and can't be really done because most of the methods that we use for testing instruments are actually contaminating them with something else and need to be rewashed. So that sort of becomes a bit of a vicious circle. But if you are looking at instruments, whenever we pick an instrument from a set and want to test it, we find out very quickly that we have to now reclean that instrument. And there are many different strategies that hospitals implement. They either take that entire set and reprocess the entire thing twice, which, you know, maybe not the most efficient way of doing it, but at least it doesn't compromise the flow of that entire set. You don't have to wait for that single instrument being reprocessed again. But it also brings up the cost quite considerably because you have to reprocess a lot of instruments twice, so you are blocking the capacity of your washers and so on. So process change devices were invented to help us out with that task because you have a little single-use device that mimics this environment. You don't really care what happens with the PCD after you've evaluated it because you keep a record of it and you know basically what happens, so your process is not disrupted and instruments can flow nicely through the department. So it was definitely developed to make a practical sense of testing. And that's one thing that is worth remembering. When you now think about the different types of process change devices or indicators that we've been using for years, it's all started with sterilization. We wanted to sort of make sure that every time we put our load through a sterilizer that the conditions required for sterilization were achieved. So we came up with those either chemical or biological indicators that were telling us the story of what was happening inside of our sterilizer. It's an interesting thing, but the sterilizers and the guys who did sterilization indicators had a little bit of help from microbiologists because the microbiologists figured out that there is actually a mathematical relationship between the organisms and the time they spend in a sterilizer or the time required in a sterilizer to get them all killed in the numbers required. So that mathematical relationship helped us greatly because you could actually say exactly what is the length of time instruments need to spend in a sterilizer. For cleaning, nothing like that exists just because you have so many different variables that make your cleaning bad or good. And this is a problem, that there is no mathematical formula that creates that situation. So the only way we can do it is to test every individual one for the presence of remaining contamination. So as a concept, we wanted to have a process change device, so a tool that presents a test that is equal or harder to what you are routinely reprocessing. Remember, equal or harder. So it was quite interesting because a few weeks back there was a discussion on Sterile Services Professionals Forum on Facebook that someone said, well, we had this PCD and I've put it under a tap and it was cleaned instantly. So then you sort of, I immediately started thinking, well, and you are still thinking that using that PCD gives you the good assurance that your processes are working fine. It was great that someone actually did that little test because they found out for themselves how they are challenging their process. So when you are thinking about the challenge to your process, you really want to think about those bloody test soils that we've discussed a moment ago. You want this to be as representative to the real load as possible. And at the same time, you have the issue of representing the complexity of surgical instruments. Just look at the pictures over here. You have a couple of examples of different grippers. They are all different. They have mechanisms inside. They have linkages inside. So there is a huge amount of contamination that can get trapped in those very fine elements. So would you like your PCD to represent that? Of course you would. So this is one that we've made, and the idea was there to actually come up with a system, not only just a flat piece of stainless steel with some contamination on it, but come up with a system that really represents the type of a cleaning challenge that you have. Test the instruments outside and test the instruments on the inside. And lastly, look at monitoring. Monitoring is the critical element that unfortunately needs to happen right after you've tested your washer. You have to find out whether what you are looking at, whether it's an instrument or a process change device, whether it's actually clean. And there are a number of different methods that you can use at the moment to evaluate whether you can still, whether you still have proteins or, or contamination on the surfaces, but it's an essential step. In most cases, visual representation of just visual check may not be enough, especially if you are talking about the tiny quantities of protein or other markers that are being suggested by our new standards. So let's jump into the last section over here, which is benchmarking and improvement, because this is something that is most important to what we do. When I was talking about the washer disinfector, you have a simple 5-washer setup, 5-level carrier setup for a washer disinfector. And I've come up with this concept of identifying your worst case scenario. So looking whether your spray arms are actually reaching your corners properly, whether right in the middle of the shelf where your spray arm is rotating, whether you have water penetrating it properly as well. So there is already a methodology that we've created that allows you to identify that, because the most important thing for you is to know, to understand your weakest links and understand where your worst case scenario for cleaning is in your washer, because you can then address it. You can then make sure that you optimize your process, you improve its performance, so you clean that worst case scenario, because if you clean the worst case scenario, everything else will get cleaned as well. So here you've got an example result. On the right hand side, you had 5 of those different locations in the chamber. This is from a real washer disinfector. We've been doing that often on different models of washers, just to identify where the particular difficulty with cleaning is. In this particular washer, the toughest location to clean was right underneath the center of rotation of the sprayer. So it's not something that naturally comes to us, because we would sort of think that right in the middle of the shelf, you should have the best cleaning. But in this particular case, it wasn't. And this is something that is really important to do, to make sure that you know what to do to improve your processes. The great thing about testing is the fact that you can also troubleshoot. You can identify whether you have a systemic problem with your system, because there are all sorts of issues that can cause suboptimal cleaning. And it's not always the process itself. There can be a mechanical failure, there can be an issue with the detergent and so on. And troubleshooting is something that we should take into account whenever we are seeing results that are not great. So when we have a result that is not great, and we have confirmed that it happens time and time again, I have created this matrix method where, by changing one variable of your washer process at a time, either by increasing the time or increasing the concentration of the chemistry, you sort of find where your threshold point is. And you can then move along that line. Why? Because it's not always best to have the fastest cleaning process, because in most cases it will require either more time or more chemistry. And then the question is, what is a bigger problem? Chemistry, more chemistry is always more expensive. More time, sometimes more expensive, but not always. And I'm personally not a great fan of super short cycles, so I would always sort of see whether you really need to improve the speed of the cycle, because as I said at the beginning, we are not talking only about a washer disinfector, we're talking about the entire thing. So you see here an example of us taking the process from, let's say, poor results to really good results, improving it step by step. This is something that once you start testing, you can do it as well, provided you have good tools to evaluate it. And that's something that I wanted to mention as well here, is that when you get to a level where you visually clean, that you can see that your process looks great, it's worth testing it with other forms that tell you a little bit more about the remaining contamination, because here you can see that even though the result looked clean, the protein sensitive reagent shown that there is still a little bit of contamination left on samples. This is almost like, you know, playing Sherlock Holmes and looking at more detail through a magnifying glass. This is what those tools are for, to give you a little bit more confidence in that. And remember, we were talking for now only about looking at testing the spray arms and how instruments are tested on the outside. The same thing needs to happen with lumens. So this is a test kit that we have created to evaluate cleaning through long lumens. And this is one thing that I wanted you to take as, again, food for thought. We have a dramatic drop of flow if we connect all of the different tubes at the same time. So it also matters if your rack can accommodate 20 or 30 instruments and you are only testing it with one PCD, that is something that really needs to be addressed, because those flow conditions are going to be different, and as you've seen before, flow through those channels really matter. And once you've done that, it is advisable to go through the same process of applying the matrix approach and to find out whether your internal cleaning is working out well. And then you can put one matrix of internal cleaning on top of the matrix for external cleaning and compare results. Last thing is loading, because what we've been discussing until this point is testing the machines on their own and finding out where the weak spots are and so on. But loading is a critical thing. And again, if you use your PCDs together with your load, you will be able to uncover how big of an influence bad loading has. Use it as a test exercise and use it to find out whether your cleaning is actually properly done. Right, guys, we are done with the content, so we are getting to a quick summary over here, and then we'll have a little bit of Q&A here. Oh, great, we have a number of great questions over here, but I'll just quickly run through the summary. You know, if there are two lessons that I would like you to take from what I've been talking about, the first one is you will not know how your process is performing if you won't test it. So testing is absolutely critical. There is no excuse at the moment for not testing, because there are many, many different tools on the market and you have easy access to them. Test it, but when you are testing and you are using a particular tool, know what it's best used for. If you are using a PCD with test soil that washes out really, really easily under a tap, then think about what it's actually telling you about your process. So those are the most important elements that we've done over here. So I'll leave you with that to ponder upon, and let's look at the Q&A.
All right, Pavel, what an incredible presentation. We had some great questions that came through, and we have time for just one of them. But not to worry.
Go for the hardest
anybody, I'll go for the hardest one. But anybody who submitted a question, not to worry. I will make sure that Pavel gets your contact information and can answer your question via email directly. So Pavel, let's start with this one. In your experience, does an enzymatic or alkaline detergent give the best cleaning results?
This is a fantastic question. I'm so glad that you've picked something like this.
Good.
Guys, there is one thing that we've tested now at least 50, maybe even 70 different types of chemicals, from enzymatics through mild alkaline enzymatics through very strong enzymatics. And you know what the rule of thumb is? That you have to have the right process for the right chemical. There is no simple distinction between, oh, enzymatic is better than alkaline or alkaline is better than enzymatic. It's the particular formula and the process you apply it with that matters. I've seen, and this is the thing that really makes me angry at times, that I see great products, great chemistries applied in the wrong way. So you use a wrong process with a great chemistry and you get bad results. This is the worst of what can happen, that you have a bad process. So when you think about chemicals, don't focus on it so much. Focus about the process and how you measured it. This is the most important thing. Make sure that at the end of that journey of that instrument through your decontamination department, you get a clean instrument that is safe to use. And the only way to do it is to properly test it. Does that make sense?
That makes sense. Absolutely. Thank you so much for providing that insight. Pavel, what an honor it's been to have you kick off the Prove It conference. I want to thank you so much for sharing with the audience this morning. For anyone who did submit a question, like I mentioned, I will make sure that Pavel gets a list of questions that were submitted along with the contact information so he can reach out to you directly. For those of you interested in obtaining a CE certificate at the end of the day, I'm sure a lot of you are. At the end of the 7th session today, you'll get a link to a conference survey. Fill out that survey and you'll be able to download your CE certificate and go into the weekend with certificate in hand. All sessions today will be available on demand. So if you tune in live for the full day, wonderful. We're excited to have you. If you have to jump off of the event at any time, not to worry. You can catch up when it's convenient for you. If you have any additional questions, you can email Pavel directly. After this session, your screen will automatically transition you to the next session, but there is a 15-minute break between sessions throughout the conference today. If the registration page appears and you're already registered, just feel free to click the already registered link and enter your email address to enter. Between some of the sessions, you'll have a chance to listen to a message from our sponsor, 3M. I want to thank you again for being here, and we will see you all in about 15 minutes. Pavel, thank you so much.
Thank you very much, everyone, for attending. And as promised, I will attend to all the questions I got and hopefully see you soon at different events.
We would love it. All right. We'll see you soon, everybody.
All the best. Take care.